Page 162 is a review and preview to Chapter 4. There are a few skills we need to practice and go over before we hit the calculus part of Chapter 4. Okay. In describing sections of the domain of a function, one of the ways we can do that is by using interval notation. The set notation is something that you've, set builder notation is something that you have been accustomed to. For example, if you want to say all the x values between a and b, you would write it like this. Do you remember this from Calculus 30? Pre-Calculus 30? If you want to say all of the values from a to b, including a and b, we would do this, right? And then we would do, hey, there's the solution, and we would do the funny brackets here, right? And sometimes they would say x such that x belongs to this part of the domain, and they might say x is an element of all real numbers. So that's pretty complicated, right? There's a lot of information there, which is all necessary. However, interval notation in calculus is often used. And instead of using set builder notation like this, we use a series of square brackets or round brackets to indicate the beginning and the ending of the interval. So for example, this right here, these square brackets are called closed brackets. And what you do is you'd put the left-hand sort of boundary, list that first, and then you would put a comma, and then the right boundary. So the domain goes from A to B, and if both brackets were square brackets like that, that means this is a closed interval. A closed interval means that it's like this. All the values from A to B, including A and B. When it's closed, it means that you include A and B. Yes, and you can think about that like this. It's a filled in or closed circle. Yeah, that's a very good way to remember it. Yes. And so if you have the round brackets, this is an open interval, and that means that the part of the domain that we're specifying is between A and B, but not including. So this one is between, x is between A and B, but not including, so no little equal things there. And this one, of course, as I mentioned, is this. Okay, so that's sort of the set builder notation equivalent. All right. If we were mapping this, right? Here's the mapping for the closed interval of A to B. The mapping here from A to B would be open circles, and then a little bit of a darkened line there, fill in, and an open circle there too. Of course, if we have something like this, A, comma, B, and this is open on this side and closed on this side, you could have that too. And of course, if we were drawing that, we would have an open circle there and a closed circle there. That's what that means. If we want to specify this right here, closed circle and everything greater than that. If this was the mapping, how would I do that? Interval notation. Leave it open. So I want to do closed A here, and then what do I put next? Well, there's no other value. This mapping says that every value that's including A and greater than A is part of the solution or is acceptable. So how do we represent going on forever? Yeah, infinity. So you would put the infinity sign here. And of course, infinity is not an actual number. It's just a concept, right? There is no number called infinity. Infinity is just, as we continue on without end. So it's always a closed bracket around infinity. So that's what that means. Everything, including A and greater than A. This is an open bracket, yeah. So what I mean here, so again, with infinity, right, there is no actual number that is infinity. So you don't really stop at infinity. It just goes on forever. So whenever you have infinity, you always accompany it with an open bracket. Does that make sense? Did I say closed? Okay, if I said closed, I meant open. Apologize. I guess we can go roll back the video and check for sure. Right? So you're probably right. I've said open and close like 17 times each already. So. Okay. Disregard the picture there. Radical. It's getting radical. Radical in your faith. How do we know about this right here? Yes, this is Jesus carrying his radical cross. Okay. Not sure why we do that.
Because we love Jesus.
Okay, good. And you guys, awesome. And you guys are so wonderful. Okay. Okay, let's try and get through this before the class completely disintegrates. All right. What is the interval notation going to be here?
Infinity,
Fill this in. Infinity, comma, b. Who agrees? I do not agree. No, you can all agree with yourselves. I do not agree. Oh, we have an idea. Thank you. Negative infinity. Wow. Very good. Okay. So interval notation, negative infinity. All right. What else do we need to talk about? Okay. You did sign analysis in pre-calculus 30. And I am going to show you how to do sign analysis again in case you've forgotten. Because we will have to do sign analysis on things like first derivatives and stuff like that to give us all kind of information, cool information. So, sign analysis. If we have, let's just say, we have a polynomial whose factors are y equals x plus 1, x minus 2, and x minus 3. I want to know where is y positive. Okay? Or I want to know this. Where is the value of the function greater than 0? And you would have to tell me which x values. Now what you could do is you could say, well, I'm going to guess, let's see, at 0 what happens. Well, that's 0 times 0. No, it's not. It's 1 times negative 2 times negative 3. What's that? That's going to be positive 6 when you multiply all that out. So hey, at x equals 0. But that's not a very efficient way of doing this. You can't check every number in existence. So what you want to do is you want to draw your sign analysis chart, and you want to put your factors here. Do you remember doing this? X plus 1, x minus 2, x minus 3. And down here, you want to put your f of x. No, it's not synthetic division. It's different. Yeah, but pretty close. No, instead, you'll remember once I start doing it. So x plus 1. First of all, you want to ask yourself, when is this factor 0? And it's 0 at negative 1 right there. And so you write negative 1. This is sort of your number line. Okay, why did I choose negative 1? Because negative 1 plus 1 equals 0. That's the 0 for this factor. So you put a 0 in line with this and above negative 1. And then you ask yourself, is this factor positive or negative outside of negative 1? So if x is greater than negative 1, like let's say 10, 10 plus 1 is 11, that's positive. So everything on this side is positive. You remember doing this with all the pluses? Oh! A chorus of O's! And then one solitary head shake. Okay. Now, just guess a number that's in this interval over here, less than negative 1, like negative 100, negative 100. What's negative 100 plus 1? That's negative 99. Party like it's negative 1999.
That's when we were born.
You were born in negative 1999?
Yes.
That almost makes sense. 2,000 years before Christ, I was born.
Yeah.
I'm over 4,000 years old. All right. Okay, might I remind you, the red light is still blinking. You guys are a bunch of jerks. Okay, I'm just going to keep doing this because the throngs of people around the world that are watching this video are not caring that you guys are, silly. So, why did I pick 2? Why did I pick 2? Jesse, tell me. Because 2 minus 2 is 0. Awesome. so 0. What am I gonna
And also.
What am I gonna write on the line here? Positive.
To the left is negative.
3.
Yeah, no, not always to the left of negative. Remember, this is a number line, so you kind of want to keep the negatives to the left here, you know, all that. This is a number line right here. But you have to actually test the number. Quick hint, if this x value is positive, then yes, it's negative here, positive there. If this x value is positive, like it is here, or sorry, if it's negative, then it would be the opposite. But you still always should test the value to make sure. So for example, at positive 3, this is 0. What happens at negative 1, let's say? Negative 1 minus 3 is negative 4, so yes, we have negatives here. All of these values will yield a negative value for this factor. Now, finally, in our sign analysis, I know a few French people.
No.
Okay.
French, the language.
Negative times a negative yields a negative. What's 0 times a negative times a negative?
Negative.
0.
Oh.
This means that the function for all x values here, all of these x values, the whole function, taking into account all of the factors, will multiply out to a negative value. At negative 1, because one of the factors is 0, the whole product will be 0. That means the function itself will be 0.
Negative.
Negative times the
Positive times a negative. These two make a positive. So positive 0, negative 0, positive. Okay. So what sign analysis is telling us is that the function is negative all the way from negative infinity, basically, to negative 1. Then it crosses the x-axis. Watch this. So to negative 1, it's negative. Here, negative 1, it crosses the x-axis. It's going to be positive up until x equals 2. So x equals 2 over here, and then it's going to come back down to 0 somewhere. Then it's going to be negative for a while, and back up to 0 at 3. See? And then ending positive. So this isn't exactly what it looks like, but it's going to look something like that. If you get your graphing calculator out, and you punch that puppy in, clear, clear, clear. Don't punch puppies. Okay, bracket, what is it? X plus 1. Look at that! Whoa! Look at that! You were off. You were off. Listen to you. That's pretty darn close right there. Look, see? Look, see? Without graphing it, we have an idea of what it looks like. Now, couple things to note. That it is ever increasing from negative infinity to 1. Somewhere between negative 1 and 2, we have a maximum point here with a derivative of 0. Ooh, that's going to come into effect later. And somewhere between 2 and 3, we also have another point where the derivative is 0 because it changes direction. It goes from 0 back up to 0, right? So all these things I want you to keep in mind as we move forward because it's going to be important. But sign analysis, very, very important. Okay, so that's the review and preview to 4.1. I'm going to give you some questions now to work on.